This is the L2 Interop Working Group, call number 15 and issue 1741 in the PM repo. We can, get started. The agenda today is starting off with fast synchronous finality, followed by some updates on the ENS-based chain registry, sync composability from SSV network, and lastly, some quick notes on L2 withdrawal windows and the 7-day challenge periods. Cool. I will hand it off to you, Roberto, whenever you're ready.
Thank you. Are you able to enable screen sharing?
Yeah, try again. Should be good.
Cool. Yeah. Cool. I think Mikhail will start on this.
Okay, can you hear me?
Yep.
Perfect.
Cool. Hey everyone. So fast synchronous finality for Ethereum protocol. Today, many systems rely on economic finality as a signal, and we all know that economic finality is slow. But the problem is that there are use cases that don't require that strong finality, and they rely on it. They have to experience increased costs and latency. And we propose fast synchronous finality as a solution to this problem. Yeah, let's go a bit into detail and break it down into 3 aspects. In the first place, it relies on the synchronous network, which specifically means that any vote that cast by an honest validator is received by all other honest validators at the end of the same slot. Finality in this context means that if block is finalized, then it will never leave the canonical chain if the assumption above and the one that we will introduce later hold. It also means that the block will be eventually finalized by economic finality. The last but not least, it's drastically fast. The block can be finalized within 1 slot time frame. We also assume that a portion of the stake can be dishonest. The max fraction of the adversarial stake that is supported by fast synchronous finality is 25%. This is a configurable parameter, and by changing this parameter, one change the trade-off between liveness and safety. So the higher this value is, the safer the block that is finalized will be. Now let's compare it to well-known economic finality that we're all used to. The fast synchronous finality is tolerable to a less fraction of the adversary, and it comes with a 0 economic security. It also relies on it has a strong assumption on the network conditions, but given all that, it's 80 times faster than the economic finality, which is roughly a 99% improvement.
Thank you, Mikhail. So just want to go over a bit high level how this fast synchronous finality works, just to give you an idea of how we can achieve this magic of 1 slot fast synchronous finalization. So just looking at this example, we have a block B10, which for now we assume is canonical, will always be canonical. I'll explain why we can assume this later. In this example, we also assume that the weight of a committee is 100. And what we want to do, we want to check if we can apply fast synchronous finalization to block B11. So in this scenario, and we are currently at the end of the slot of B13. So in this scenario, we have that 80, we have a weight of 80 in terms of LMD votes for B11 and 85 for its child B13. So overall, the support that B11 has received in terms of LMD or head votes is 165. And in order to be able to fast synchronously finalize B11, what we want to do, you see it on the right, we want to check that the support of B11 is larger than half of the maximum support that any child of B10 can receive, so either B11 or any of its siblings. So more than half of this, plus the maximum adversarial weight, that dishonest weight that might have supported B11. And this is because this dishonest weight might be taken away because it's dishonest, and so dishonest validators might give the weight to B11 and then take it away. So by removing this, we still want to make sure that B11, the weight on B11 is larger than half of the maximum possible weight that can support any sibling of B11. So so that the maximum possible weight essentially is the weight of the committee from the slot of B11 till the point where we were on FSF, plus this proposal boost, which is an extra 40% of a committee weight that is given to a timely block. And you see this in the formula. So if one substitutes everything, we end up with a threshold of 160. So in this case, the support for B11 is 165, which is more than 160. So we can fast synchronously finalize B11. This is just to give you an idea of what we do. We essentially count attestations, and we have quite strong conditions to ensure that when we fast synchronously finalize something, it is actually going to be always part of the canonical chain, of course, assuming synchrony.
Well, I think you're muted, Roberto.
Thank you. As I said, we assume that the say B11 is canonical. We can do this if say B11 is the latest economically finalized block. So then we try to fast synchronously finalize its child, which is B11. If we succeed, then we know B11 will always be canonical. So we can do the same to its child, and so on and so forth. So that's very high level how this algorithm works. We have been able to run some preliminary performance measurements. Now these are on proof of concepts. We ran this for a day, for 24 hours. And the results we got are, in my opinion, pretty good. Like in nearly 95% of the cases, we've been able to fast synchronous finalize a block in one slot in less than 12 seconds. For 2 slots, we go up to nearly 99% of the times, and then above 99% for being able to fast synchronous finalize a block in less than 3 slots. And as you can see, it just in 7-8 slots we get to 100% of the time, which is, so if you look like, less than a minute we are basically there to 100%. And one comment on this long tail, we think is due to late blocks or blocks that have where the slot of the parent is not the slot before. So there is between the slot of a block and the slot of the parent, there are empty slots. And this, because of the rule, this can impact the performance, but we are working currently on an improvement to mitigate this issue, but we haven't been able to to run the measurements on. So we hope that we can get even better results than these results. So just I want to conclude just giving you an overview of where we are, what the next steps are. So we currently have a draft specification and a proof of correctness. There are 2 proof of concepts in Takeover Lighthouse that are tracking the latest spec. And there's also a proof of concept in Prism that is implementing a portion of the specs. We have, as I've shown you, we have some preliminary performance measurements and also working on fixing this empty slot case. Next thing is finalizing what we have currently going on, writing spec tests. We want to get more measurements. We want to get some of the proof of concepts to production and eventually have fast synchronous finality implemented in any client. And importantly, there is no hard fork required for fast synchronous finality. It's essentially there are changes that have already gone in a long time ago, and it's an algorithm that can be applied just basically by analyzing attestations, as I've shown you before. So with some references, we share the slides later for you. And this is all. Thank you, and open to questions. Trying to stop.
Orest?
I guess I'd have the same question as Marcin from the chat. Like, I also I really like the idea, and great to see this being pushed so badly. And yet I still struggle a bit with my mental model of how much stronger the assumption set for FSF is over economic finality. Like what Francesco is saying, okay, like an FSF final block will eventually be finalized, assuming the assumptions hold, but we are kind of having this beta of 25 instead of 33.
I think you frozen. You froze. Huh?
Maybe we can come back to Orest. Any other questions in the meantime? Oh, okay. You're back, Orest. We lost you for a second. We heard the first part of your question, but the second half we missed.
Yeah, I'm sorry. So basically, I'm struggling to develop an intuition for how much stronger assumptions we would be introducing with FSF. Like my gut feeling is it's like 25 or 75% of the nodes are non-Byzantine versus 67% are non-Byzantine. So a slight increase in assumptions. Is that adequate?
Yeah, for what we have at the moment, yes. Like in a way, it could be possible to so that the reason why we have this 25% is that if you have a higher threshold, the adversary can just prevent fast synchronous finalization of any block just by not doing anything. And now you don't see any progression in fast synchronous finality. You don't know anymore whether it's because the network is bad or that's where the adversary is just not cooperating. And that's really why there is, in theory, for safety only, you can go up to 33%, but then again, you enable the adversary to prevent the algorithm from working.
Yeah.
I think maybe another note is that like this definitely doesn't replace full finality, and like there'll still be use cases that should probably wait for full finality. But I think for a lot of use cases today, this is actually stronger than what they do. Just like a lot of use cases today do not wait for full finality and instead just wait for like block confirmations. And FSF is like a lot stronger for that anyway. But yeah, some use cases should still wait for full finality if they don't feel comfortable with these trust assumptions.
Would it be fair to make this mental exercise? We could require that all nodes be synchronous and only treat a block as fastly synchronously finalized once, let's say, 99.9% of the previous validator said that was online attested to it. Like this would be almost the same level of certainty, but still probably doable in a couple of blocks rather than in 13 minutes.
So
What
I
do you mean to?
So what you're describing it kind of reminds me of, I guess, what you describing saying like, you know, the entire stake of an epoch would like vote on a
Yeah.
block.
Yeah.
I mean, I think that's possible. I guess it's just a very different paradigm of what we have now, where like only a committee votes on each slot, and then you get the entire stake over the epoch.
Hmm.
Yeah, and then what you're saying basically, you need to wait the entire epoch, right?
Hmm. Right, I see. It's because of the committees that we can't make this mental exercise. Yeah, makes sense. Gotcha.
But I mean, I do
Like
think. Sorry, go ahead.
I would say, like, if you want to do that, if you're happy to wait for an epoch, you essentially you can just at the beginning of an epoch, you can first synchronous finalize what was the greatest analyzed checkpoint that you saw in the previous lot. So you could do that, and that's safe against 33%. So
maybe in the context of what you have said, in the context of your mental model, if we like say that the block is final, we need synchrony to all other validators to vote on it in all further slots, you know, so that it will get much more weight. This is like one of the places where synchrony is required, where we rely on the synchrony in this case. Once the entire validator set votes on it, that block is will have like a lot of weight, which will be difficult to get through to rework out. So and yeah.
Ian?
Hey, my question's in a bit of a different direction, so I don't want to interrupt if this conversation is continuing. But if not, the question is, so in the context of L2 interop, this is, like, as an interop protocol, if I want to use this, I have to be able to verify this finality mechanism on the L2s, which I think should be trivial. You know, you can hand wave away that problem of just saying that you can use a snark to verify this finality gadget inside of an L2 execution environment, but you need a public input to verify it against. So we still need that L1 origin view, or L1 S load or something to actually verify this finality gadget against inside of the L2 execution environment before it's actually like useful for interop protocols, like on-chain interop protocols. It's still useful, obviously, for like node operators and other off-chain activities.
I mean, yes, you're right. Although I don't think it would be any different than needing that information today. Like I don't think it introduces anything new than just today you also need a way to verify like the state of the L1.
I completely agree. I just feel like this is still something that's like kind of neglected in these conversations, is that none of this really matters until that's solved.
No, yeah, it's a good point.
Other questions? Cool. If not, we can move on to the next agenda item. Thank you, Roberto, Mikhail, for the presentation. Actually, before we move on, Ellie, did you have anything else that you wanted to add on this topic, just in terms of sort of, I don't know, potential roadmap and next steps?
Yeah, so if those of you who don't know, I have recently joined the Ethereum Foundation, and so my first task is that I will be working on fast synchronous finality. So as part of that, I will be reaching out to a bunch of people in this group to kind of get feedback on it, to see, you know, how best different projects are able to use it and how it can benefit them. So yeah, look for that.
Awesome. Thanks, Ellie. We are excited to have you. Cool. Up next, some updates on the ENS-based chain registry from Unruggable and Wonderland. Yeah, anyone from Unruggable want to jump in first?
Yeah, I'm here. So my name is Martin, and I'm representing Unruggable. We've been working.
Did we lose Martin?
Bad Wi-Fi day today.
That is typical that Martin has just his Wi-Fi failed. He's in Nairobi, Kenya, so I know that they have notoriously bad Wi-Fi. Oh, is he back?
Wow, is it? Can you guys hear me well?
Now we can.
Better, I think, yeah.
Now you can. Okay, let me get started then. Sorry about that. Okay. Sharing my screen. Great. You can see my screen?
Yep.
Amazing. So, well, as I said, my name is Martin, and I will be taking us through this Ethereum chain registry. So, starting with
Thomas, do you maybe want to jump in while we wait for?
Yeah, absolutely. I know that Martin's internet in Nairobi, Kenya's notoriously unreliable. Hopefully people can hear me and mine is working better. I was expecting Martin to do this, so I don't have the presentation up, but I can just kind of give Martin, you keep
my
on.
network is still bad.
Yeah, we lost you again. If you want to give it another shot.
I'm so sorry about that.
No worries.
Okay, so where were we? Let me try one last time. Yeah, I was saying we first explored ERC 7785, which was proposing a 32-byte chain identifier, which will be derived by using the chain name itself, along with some auxiliary attributes of that chain to derive that chain identifier. But in the work that we've been doing, we've come to realize that we can achieve the same result without having to use the 7785 identifiers. And the path that we have chosen is to have these human-friendly chain names like, optimism.cid or whatever ENS domain will choose, resolve to a 7930 identifier. So I'm going to send a couple of links from the chart that contain the original specs and as well as 7930. And yeah, so the purpose of this is just to have registry that can resolve from this human-friendly name to a 7930 identifier and back. So we have 3 main contracts within this registry, and we have the chain registry, which is the source of truth. This links the chain label to its own record, and lookups in this case are keyed in, or rather the main lookup would be the hash of the label, which we're calling the label hash. And we have the chain resolver on this other end, whose work is to return the chain, the 7930 identifier from the label, and the reverse chain resolver, which does the opposite. It takes the 7930 identifier and it returns our chain name for us. So these 3 main contracts make up the chain registry. And if you look here, this is the architecture. I have mentioned that the registry here is going to be the source of truth, and we have both resolvers, the forward resolver that returns the 7930 identifier and back, both of them refer to the chain registry as the source of truth. And that takes us to the chain registry itself. So this registry, in order to work with these resolvers, it needs to expose these two functions. That is the chain name and the chain ID. This interface is what the resolvers, both the forward and the reverse resolver, use to work with this chain registry to return the information that we're trying to pull about this registry. And moving on to the next contract, the chain resolver. This returns our 7930 identifier given the label. And the chain resolver is an ENS resolver that is fully compliant with the ENS spec, ENS IP10. And what this means is that we can use this resolver and the chain name that we will give, for example, base.cid.eth, to be able to set and resolve a specific type of ENS records. We can
I think we have once again lost Martin, so I will just jump in again. Thomas from Unruggable. I've posted links to these slides and a demo, which kind of demonstrates this end-to-end in the chat, so people could kind of look at this directly, as well as a link to our Learn page on that demo that links to all of the sort of external material for anyone that sort of wants to upskill in terms of ENS specific specifications and architectural patterns. But the short version is that, kind of having conversed with the Wonderland team, who did kind of lots of work in relation to these kind of resolver concepts previously, we've kind of essentially built an ENS resolver that allows you to resolve a chain name as a subdomain of an ENS name to its 7930 chain identifier. Our intention is to kind of document this within the Ethereum Foundation's Interop repo and kind of request feedback and commentary from the community here. And we're also going to kind of piece together a post to post on the ENS forum to get insight from the ENS community as well. Unruggable's context is obviously ENS, so kind of we're hopeful that sort of we've architected this correctly from the get-go, and kind of we've discussed with various aligned stakeholders. But yeah, in the interest of sort of opening this up to the community and making sure that we get this right first time, we want to sort of at least have a brief period where we welcome external contributions. But in the grand scheme of things, this is actually sort of quite simple conceptually. So we're hoping that we can kind of move this along quite quickly and have a kind of solution that people can integrate with that allows for resolution of chain identifiers on chain, as opposed to utilizing centralized resources like we do at the moment. For example, the GitHub repo, etc., etc. I don't know if anyone from the Wonderland team wants to kind of add some additional context from their end. Of course, I'm happy to answer any questions as well.
Sure, I can add just two extra things. First of all, thank you to the Unruggable team. They've been shipping great improvements to all of this, and they're basically getting this ready to be finally deployed and accepted by the ENS DAO as well. So besides that, one note to take into consideration is that both the registry and the resolver use 7930, but 7930 is not enshrined neither on the register or the resolver. the main idea for this is, for now, we are going to be using 7930 as it is the standard that we currently all agree on. But in any case, in the future, that we might end up with an improvement or modification on how do we, I don't know, signal or identify chain IDs. Obviously, this what we've all built is it's dynamic enough for us to be able to switch to whatever other standard in the future. Also, and this is kind of important, maybe Josh, if you want, you can also comment on this a little bit, but the migration process from GitHub to Onchain has a script that we developed. We can share the repo later. It's a simple script, but the important thing here is for any chain or chain operator or whoever that wants to set a new name. I know some of the names some teams might want to change. They should do that as soon as possible. Hopefully, Josh is going to be contacting some of you just to try to get those changes in place, and we'll have a simple flow for you to communicate those changes, so we can basically get a clean migration with let's say cute or nice names over on chain, which might be way more difficult to change in the near future when everything hits mainnet. Also, one thing to note, you might be asking, hey, what's let's say the ownership or governance process of modifying all of these domains or handling this second level domain? Those are still undefined, and we'll have more comments on that later. But it's the important thing is to just move forward, do this first step, migrate everything over on chain, and then we can also experiment on different ownership mechanisms to handle this registry and resolver.
Thanks, Kelly. Yeah, sorry, Thomas, if you had something.
Yeah, I was just going to say, kind of to add to what Skele said there, our initial intention is to kind of set up a multi-sig of some sort with community stakeholders, and that will kind of be outlined in our specification within the Interop repo and on the ENS forum, and kind of we welcome feedback on who people would like to see on that, but we want to kind of do this iteratively. That will be sort of a get this out the door multi-sig, and obviously ownership can be transitioned over to a different model as appropriate. The only other thing was I saw that Massimo asked a question in the chat about ENS resolution. ENS has kind of adapted over the years, and there are more ENS IP specifications. So there is kind of forward resolution, and there's reverse resolution, which is also kind of often referred to as primary name resolution, whereby you can kind of resolve the ENS name associated with an address. In the context of this, it's conceptually somewhat different in that we want to, for example, resolve base.l2.eth to a 7930 identifier, but we're not trying to kind of reverse a address back to a primary name, so it doesn't strictly fit into the kind of primary name paradigm. So that learn link that I posted on our demo does kind of outline a number of sort of ENS IPs, which are essentially specification proposals for ENS specifically, that allow for this kind of new paradigm whereby you can pass in a 7930 chain identifier and get the string representation of a chain back instead. And yeah, similarly, ENS IPs, kind of from my experience, it's people propose them and then implement them. And if the implementation is good, people copy, and then it becomes enshrined as a specification. So we're hoping that kind of we could demonstrate this as a productionized use case that kind of proves the value of the specifications we're proposing. And then over time, they will become enshrined.
Perfect. So yes, we will be reaching out to L2 teams to coordinate on some of this. I see there's a few L2 teams here. If anyone has questions or thoughts that they want to share right now. Otherwise, we can, yeah, maybe leave it there.
I have a question, and this so is this still just related to L2 chain IDs, or is this like from the get-go extended to all L1s and even on EVMs?
Yeah, the intention is to support all chains.
Okay, wouldn't like have a .eth extension be kind of biased in this? I don't understand, like people would just use like solana.eth to, I don't know, sol.cid.eth to reference something. Maybe a new extension name would be more, less biased. That's like
I
a
think
.cid.
Yeah, I think Skelly mentioned that that there's maybe ways around this, and I think our primary, like our goal is to support all chains. At the same time, our primary focus is within the Ethereum ecosystem. We're not attempting to force or to necessarily sort of make sure that we are coordinating with all ecosystems here, but we do want to at least be compatible and support any chain that wants to be compatible. And yes, I think Simon also mentioned that there's other ways that other chains are compatible. So yeah.
Okay, makes sense.
Okay, cool. Well, just so that we're a little short on time, maybe let's go on to the next topic, which is SSV network and sync composability.
Hi, everybody. I'm going to start sharing my screen. Hope the Wi-Fi curse does not hit us again. Sorry. I already started on the wrong foot, sharing the wrong screen. No, yeah, you're right. Okay. So this is the request to speak was actually kind of like an introduction of a new project that the SSV network is working on, and we named it Compose. Like it's essentially an explanation of how we went about it, what we studied in order to create it, and what it tries to solve. Starting with, this is the table of contents. Quickly, we're going to go through the where we started with the functionality that we want to achieve, which is the Ethereum composability, and extend it to the L2s. And then the UX research that we did, the summary of it, at least for brevity, and the comparison between asynchronous and synchronous composability, research we did on existing solutions, and then our own solution, like our own, we think, improvements upon it, and a quick overview of how it works in practice. So starting with, I think, what most of us in here are already familiar, Ethereum composability is essentially the ability to create, compose basically, like Legos, using like functions from some contracts and create a new contract that basically uses them once again like Legos. The best part about this is that wrapping some function calls in another function call makes sure that when a user actually calls this one, it has a guarantee that this will execute somewhat atomically, so all or nothing. And most importantly, synchronously in the same block. So this is very powerful. It's obviously the reason why, one of the reasons why Ethereum is successful. Like in reality, visually, it looks like this, where I can compose one single function call of many others, and they all belong in the same block, like I said. Separated from all of this, like this is basically what I just talked about, is the North Star, the target of what we want, sort of like the UX they want to achieve, we wanted to achieve, and extend it to the L2s, which is exactly the opposite at the moment. We're going to see that later on. But the next section, at least, is going to be about the UX of what are the tools currently available for achieving this, or at least what the tools can do to facilitate this in some kind of way. And it mainly focuses on two things: making like allowing developers to create multiple calls and put them in a single transaction, and then targeting multiple chains in a single go. It can be either one or multiple transactions, but in a single, let's say, user interaction, so to speak. And the result is I skipped a lot of slides that I presented in a different call just for brevity, but the result is that we have account abstraction, ERC 437, which basically works well if everyone switches to smart accounts, because the bad side, the negative side of it is that users, like the smart account has a different funding, and so there has to be some transfer of funds, which is another transaction that a user is forced to sign, or it's not ideal in any way. The other thing is security concerns, because user operations are signed using ETH sign type data, and the user is signing on a hexadecimal string, not knowing exactly what they're signing off on. EIP 5792 is wallet send calls, the additional wallet RPC calls, which basically it lets the wallets decide how they want to support it. It's just a request of, hey, please batch some of these calls in a single go, but it doesn't tell wallets how to do it. The best result that we saw was MetaMask implementation, which under the hood actually uses EIP 7702, which is setting the user's EOA code to an external contract, which basically it's kind of like a mix of the two a little bit. It's by delegation, by virtue of delegation and allowing the user to sign an authorization, you have a contract living, quote unquote, inside of the user's EOA, and then there's no movement of funds because the singleton entity is kind of like using natively the funds of the user's EOA. But the problem is this is not usable on its own because there is no RPC method to sign the authorization. MetaMask is able to do it because it's an internal request happening within the wallet's backend, and so they're kind of cheating in that way. And so it's also like why EIP 572 is kind of it's gated, right? Like MetaMask can't do it because they're a wallet. Like if I want to build a web app using EIP 772 at the moment, I cannot. For the second part, the targeting multiple chains, it's important because if I want to achieve our goal, which is synchronous composability, the two different rollups or L2s need a way to correlate what are apparently two independent transactions. And we have not found we haven't found any solutions for this, essentially, which is why in the end we'll see we have come up with our own. Now, quick overview of what is currently what was currently available in terms of composability, and it's asynchronous composability, whereas the ability to compose different, let's say, intentions from the user point of view are made possible asynchronously, and this is why the finality that the presentation that was made before is actually comes into place, because the several minutes waiting or delay can be reduced using that, but it's still going to be a delay, and it can only be reduced so much. And most importantly, it doesn't guarantee the atomicity. Like if anything breaks in here, there's no way to reverse the course of actions. Whereas what we want to achieve is this, the confirmation that these actions are part of the same L2 blocks, and they're going to be part of the same L1 block as well. And if one of them fails, like nothing is going to be pushed to the L1. The way we went about it is by studying Espresso's circ. So we're talking about mailbox contracts that allow for sequencer to sequencer messaging. And this way, basically, the two sequencers can simulate the execution of function calls, and they have to agree on essentially the number of messages exchanged, or more importantly, the status of them. I think this one is a better, like, more visual representation of it. So when on rollup 1, I lock some funds, I then send to the outbox the fact that I have locked them. And so I request for the rollup B to mint on the equivalent on their side. And so when that happened, on rollup B, I can also chain the request to trade them or do something like put them in a lending pool or whatever. And then when I want to, let's say, this is an example of a flash loan, for example, right? So on the return, once I traded it, it's a swap, not a flash loan. Once I swap them, I want to send back the funds to rollup A, and so I do essentially the reverse action. I lock them first, and then send on the outbox the fact that I want rollup A to mint. Rollup A finds this message on the inbox, and now the inbox and outbox are specular, so the simulation is confirmed. And I think we have I'll get back to that slide later on. But essentially, once the sequencer have gone through the full simulation, it has the confirmation that the blocks can be, so that the function can be included. Like I said, this is probably not new to some of you, but previous solutions were using a shared sequencer, whereas with our solution, we use a shared publisher, and the sequencers remain independent entities. So there's no request to sort of like change current L2, infrastructure or the way they design their own L2. Most importantly, the shared sequencer is a form of centralization, and it also brings itself to scaling issues where with our design, we think that this can be overcome. Essentially, it basically is an extension of Circ to a means for distributed coordination amongst sequencers. This is, like I said, I already kind of explained it, but the important part is that at the end of the simulation, the sequencer sends a vote for signaling the fact that the simulation went okay. And when the shared publisher has enough votes, it sends back an acknowledgement that the decision has been reached. We call this our agreement algorithm two-phase commit. And at the end, they basically send back their own block, and the shared publisher is in charge of publishing the block to the L1. I said that we came up with our own solutions because eventually, like I said, the two rollups have to find a way to recognize what could be looking like two independent transactions as actually belonging together. So the fact that they have to kickstart this simulation phase, and we came up with a custom RPC call that the sequencers implement, and it's essentially as we see here, like the identifier of the chain and the transaction itself. The problem that we found ourselves is that obviously the transaction has to be signed, but commonly a web app cannot sign it because the methods to do that are like deprecated or forbidden. And we turned ourselves to signed user operations because at the moment it allows the user to sign the user operation as a message, and then the transaction that sends the user operation to the chain is a different thing. And so we have another custom RPC method on the sequencer that basically takes a user operation and signs the transaction that should include it. And the conjunction of these two makes it so that basically the output of this compose build signed user operation transaction method is a signed transaction. And then you can use basically the output of this one as the input of this one, or making up the payload for a cross-chain transaction. Then the sequencers are able to identify the user operation as a cross-chain operation, and they start the simulation basically. Like I have skipped the minutia of the ZK proofs, but of course, like upon reaching consensus, they also send a ZK proof of the simulation itself. The shared publisher packages up the multiple proofs into an aggregated proof to the L1. And where there is room for improvement, we have improved. We think that we have improved by using user operation and allow you basically to compose like Lego bricks, not by building custom contracts, but by mixing and matching contract calls into a user operation. And the problem that we found is that what I already mentioned, current account abstraction solutions have significant drawbacks, namely the funding, but also the fact that what the user is signing is not very intelligible. In our opinion, in my opinion, it would be much easier if a signed authorization RPC would have been implemented and supported. This would basically abstract away the funds movement, and it would act as if the user is natively accessing a smart account from their own EOA. Yeah, I think this is it. Thank you for listening.
Thanks, Massimo. There is a question in the chat from Ed on the trust assumptions of the shared publisher. Do you want to maybe share a few quick?
Yeah, sorry, opening up the chat, which is incredibly small when you're sharing the screen.
The question is, what is the trust assumption about the shared publisher?
Yeah, go ahead. Oh, sorry, Alan.
Hey guys, Alan from the FSV team. So the shared publisher is, as the name suggests, only publishes, meaning that if the shared publisher fails, the rollups themselves will be able to finalize by settling on the L1 independently. Of course, for cross-chain transactions, that means that there's no coordination layer for that. They can still do cross-chain transactions, though the actual checks for the mailboxes is done by the shared publisher. The shared publisher is important to say it's going to be based on Ethereum validators. It's not a centralized entity. So Ethereum validators will be the one running the shared publisher code and actually be the shared publisher.
So that's an assumption about liveness. Are there assumptions about things like non-equivocation?
What do you mean? If you can give an example.
Yeah, so suppose that the shared publisher tells chain A, the message you sent was delivered to chain B, but it tells chain B there was no message sent.
Oh, no. So the shared publisher is not telling anyone anything. So the shared publisher is, when they do the simulation, the sequencers, when they do the simulation, we're using a 2PC consensus protocol. The shared publisher is the coordinator of that protocol. So they know the origin and the destination of the just the coordination phase or the simulation phase. The shared publisher main responsibility is to just produce an aggregated proof of the different chains. And inside that aggregated proof, we also add mailbox proofs. So that's the responsibility of the shared publisher. And again, the shared publisher is not a centralized entity. It's going to be based on Ethereum validators. And so there is no trust assumption on like the shared publisher can fake it because he needs to produce ultimately a ZK proof. Now there is liveness challenges there, but maybe the shared publisher didn't produce any proof. That's why we're building it to be based and not a centralized entity to mitigate that as much as possible.
Right, but what if it produces two different proofs that prove that two different possible histories? That's the equivocation question.
Oh, God, so two different histories, you mean?
Yeah.
So again, each sequencer is responsible for producing its own proofs and its own blocks. The shared publisher is not producing blocks on the behalf of the chains. It's passively receiving those blocks from the sequencers and then produces blocks. Produces an aggregated proof for them.
Let's take this offline.
Sure.
So we just have 3 minutes left. Or as I see your hand is up, is this something that you want to get to now, or should we move it async?
Just super briefly, this shared, like non-shared sequencing model would still require the individual sequences to have opted into the system, right? To actually consume, like use Circ, use the mailboxes.
Yeah, so we differentiate between two types of rollups. Type 1 is integrated rollups, meaning that they fully integrated into the compose layer, meaning that they produce ZK proofs, and the share publisher takes those proofs and aggregates them. There's another type of rollup called included rollups. Maybe the naming should be better, but included rollups are rollups that we did not choose to integrate into the Compose network. Rollups, for example, like Base or Optimism and Arbitrum, we can enable synchronous composable transactions between integrated and included rollups, but we cannot guarantee, obviously, synchronous composable transactions between two included rollups, because two included rollups cannot roll that. Or they don't guarantee atomicity. So that's kind of, there's two types of rollups that can play along in this protocol.
Thank you.
Thank you, Elon and Massimo.
Thanks, so.
Yeah, sorry. I guess we can we can end it there. Just, I guess, for the last agenda item, I'll just cover really quickly in the final minute here. Topic is L2 withdrawal windows and reducing the 7-day challenge period. I guess just a couple of super quick notes. Yeah, as many here know, this is something we have by design on optimistic rollups to protect against strong censorship attacks, but it's also a bit of a bottleneck on UX and Interop. So we are exploring designs and potential paths to reducing this 7-day period to something like potentially 1 day. This isn't the first time that this topic has been brought up, of course, and want to make sure that we do this in an informed and secure way. There is a reason why we landed on 7 days. So I think that, yeah, hope to organize some discussions on this topic with L2 teams, the folks over at L2 Beat. This is really just sort of an open invitation for feedback and anyone who would like to participate in these conversations. Yeah, so just wanted to flag this here quickly as something that is on the radar as well. And if anyone has anything to, I don't know, want to chime in the final 30 seconds here on this topic. If not, we can continue this on the next call. Cool. Okay. Well, then let's end on time. Thanks all for joining. See you next time.
Thank you. Bye.
Thank you for having us.
Thanks.
Yes.
Bye.
All right, guys. Enjoy your sprint planning.